In these examples, we're going to practice the chain rule. And for part A, we're given that r of q equals q cubed minus 5q plus 7 quantity to the 5th power. So when we talked about the inside and the outside, or if we're thinking of the Leibniz, what is the z? Sometimes it's easiest to think about the outside as the last thing you would have to calculate, or the last button you would have to press if you were doing each step individually for your calculations. And in this case, the last thing that we would do is we would take all of this stuff, whatever that answer is, and take it to the 5th power. So I think of that as my outside function. And this as the inside function. So I'm thinking of z is q cubed minus 5q plus 7. So if we use the chain rule, we're going to have the derivative is going to be the derivative of the outside times the derivative of the inside. And I'm going to, so let me rewrite this, that we're going to think of this as y equals z to the 5th. And we're going to use the chain rule. R prime of q is going to be dy dz times dz dt. So when we think of it this way, we're going to have dy dz, using our power rule, is going to be 5z to the 4th. And then dz dt, dz dq, not dz dt, because q is our variable here. So that's why, again, when I think of the chain rule, I think of just derivative of the outside times the derivative of the inside, rather than memorizing something with Leibniz notation, because then it doesn't matter what letters we have. And so we have derivative of the inside is the derivative of all the stuff that's in the parentheses in this case. So we would be looking at 3q squared minus 5q. Derivative of the plus 7 goes away. Now, if you were to type this in as your answer, this wouldn't make sense, because what does z mean in this context? No one knows. They're not, the computer's not going to expect a letter z as part of the answer. So we have to go back and rewrite this as 5, what was z again? It was q cubed minus 5q plus 7, all to the 4th. And then we have 3q squared minus 5q multiplied. Make sure you put parentheses around all of these pieces. All of this is multiplied. If you forget the parentheses here, it'll be a very different answer. So this problem actually follows a pattern. We're using the outside function as a power rule. We're taking some stuff to some power. And using the chain rule, that always has the same pattern. So what I like to write is we have the power rule plus the chain rule. If we're looking at y equals some stuff to the n power, then using the chain rule on this, y prime, the derivative of the outside would be, here we'd be thinking of z to the n power. I'm not going to write that down. We'd have n times that stuff to the n minus 1. And then we'd have times the derivative of the inside. Okay. So a less technical way of writing it, if we're thinking of this as a bunch of stuff to the n power, we'd be n times that stuff to the n minus 1 times the derivative of that stuff. So let's look at this idea on part B. For part B, the first thing we should do is rewrite it. we want to rewrite the radical to 3 plus 5x squared to the 1/2. And then since it's on the bottom, we want to write it as 17 times the quantity 3 plus 5x squared to the negative 1/2. Gets rid of the fraction, which is really nice. And we see that this is similar to this. The only difference is n is a fraction and actually a negative fraction. So using the chain rule, we have h prime of x would be 17, and then bring down the exponent, negative 1/2 to the of that stuff. And then we subtract 1 from the exponent. So subtracting 1 from here, we'd have negative 3/2. And then we have times the derivative of the inside. Derivative of the inside would be 10x squared. So let me rewrite this a little bit. We can simplify this more. We'd have negative 17/2 3 plus 5x squared to the negative 3/2 times 10x squared. We could rewrite this as a fraction, put radicals. We could combine this even more. But again, this is from the derivative of the outside. This is from the derivative of the inside for the chain rule.